Hi, everybody. We're doing some properties of groups, and this is section 11.3. So first, identities are unique. So what does it mean, identities are unique? The identity of a group is unique. And what specifically does that mean? So here we're going to rephrase it. This is very important that we do the rephrasing. And we're rephrasing it just in a way that's going to be more specific. Why can't I highlight this? More specific and make more sense, therefore. I'm trying to highlight. Oh, here we go. I don't know, I was having so much trouble. All right, no, I'm not going to waste it. So here's the rephrase theorem. If G is a group with an operation star, and E is an identity of G, then no other element of G is an identity of G. So there's only one identity, and that's it. And we're going to prove it. We're going to do an indirect proof. We're going to suppose that there is an element F. F is an element of the group G, and F is different from E, it does not equal E. And we're going to assume that F is an identity, meaning that if I multiply something times F, I get the same thing. We are just going to show now that F has to equal E, which, why? Because if F is equal to F times E, because E is an identity, but F times E is equal to E. So F equals E. So we see that there's just one identity, and that's it. So every group has one and only one. So we said that groups have to have an identity element, but we've proven that there can only be one identity element per group. That's a nice thing. Further, inverses are unique. The inverse of any element in a group is unique. And this has to be proven, and it has to be restated. It has to be restated or rephrased, I should say. So let's rephrase this in a way that it's going to make more sense. Okay, here we go. So here's what we're going to say. So for 11.3.3 rephrased, let's assume that A, B, and C are all elements of a group G with an operation star. So what I'm saying now is that if A star B equals B star A equals E, and A star C equals C star A equal E, then B equals C. In other words, B is an inverse of A, and C is an inverse of A, so B and C must equal each other. And that's the way of saying that inverses are unique. So let's do it. So first of all, let's prove it. So first of all, A star B equals A star C, because they both, and that's really because they both equal E. And that's number one. Now I'm going to multiply both sides by B. So B star A star B equals B star A star C. Now I'm going to move the parentheses around because we do have associative property in a group. I get B star A star B equals B star A star C. But B star A is E, because that's what we're saying here. We're saying that B star A equals E, because B is an inverse of A. And I have that in this parenthesis, and I have that in this parenthesis. So this becomes EB equals EC, but EB is just B because E is identity. That's the property of identity elements. And EC is just C, so we have B equals C. So we see that A and C were both inverses and PAL. I'm going to just spell that out more in the theorem. Let's see if B and C are both inverses of A, i.e. A star B equals B star A equals E, and A star C equals C star C equals E, then B equals C. That's really what I'm trying to say. That's my rephrasing. I'm just spelling it out more clear. That is how we do that. Yay! Let's go back to the textbook. So that's 11.3.3, and it's re-explained. Now let's look at some inverses here. Now, once we know that inverses are unique, we could use the term A inverse. You see, I couldn't use that terminology A inverse because it would be ambiguous. Which inverse? Maybe there's 25 inverses of A. But now that we know there's one and only one inverse, I could use this notation A inverse. Anyways, E inverse is the inverse of the identity element, which is always E. That makes sense. A inverse inverse, which is the inverse of A inverse, is always equal to A. That also makes sense. And that's you see that in theorem 11.3.5. If I have a XYZ inverse is the inverse of XYZ. And that's going to actually kind of wind up equaling Z inverse times Y inverse times X inverse. That's so you see that in other linear algebra, you see that in other places. Okay, so let's look at 11.3.5. The inverse of an inverse. So we need to, again, rephrase it. If A has an inverse B and B has an inverse C, then A equals C. If A has an inverse B and B has an inverse C, then A equals C. So let's say, so we know that A is equal to A times the identity, because the identity doesn't change things. And A star B star C, because we know that C is the inverse of B. So A is equal to A star E, which is equal to A star B star C. That's what we're saying up here, that they're inverses. Now by associative, I can move the parentheses. So A star B star C. But A star B is also equal to E, so that's just equal to C. So we have A equals C, which is what we're trying to prove. Yay. Okay, now, if you have the inverse of a product, that's the reverse product of the inverses. And this is very easy to prove. This you see this. You see this in linear algebra. If you took it there, you see it in a bunch of places. Anyway, if X is equal to B inverse A inverse, and I multiply that times AB, look what's going to happen. If I have AB times X, I get AB times B inverse A inverse. I'm basically going to jiggle around the parentheses until I get this down to the identity. So X is the inverse of A star B, and we know that inverses are unique, and therefore that is the inverse. Therefore, this is the inverse. And which leads us to the next thing, which is cancellation laws. Now, they know the cancellation does not always work in linear algebra, but here we're going to see something else. If A, B, and C are elements of group G, then you have what they call left cancellation and right cancellation. See, because it's not always clear. We're used to canceling when we do like old-fashioned high school algebra or whatever, and we have equations we cancel out. We don't think it's on the left side and the right side. We just cancel. If it's on one side of the equation, the other side of the equation, we don't think of it. But here we're dealing with groups which may or may not be a billion. A billion means commutative. They may not be commutative necessarily, so we have to distinguish left cancellation versus right cancellation. So we're going to prove the left cancellation law, and the right cancellation will be proved the same way. So I have here AB equals AC. So AB equals AC, and we're going to multiply both sides by A inverse. And then I'm going to shift the parentheses around, and the A inverse A is going to disappear, so we're left with B equals C. So which is what we're trying to show. So if AB equals AC, and so what you do is you multiply both sides by A inverse, and you want to get B equals C, which is cancellation. Like when we cancel, stuff in an algebra equation. Speaking of algebra equations, let's talk about linear equations. So you can have a linear equation. Now we always say linear equations with regular real numbers and all that, but a linear equation, you can have that in a group. So G is a group. Then the equation A star X equals B has unique solution X equals A inverse star B. In addition, the equation XA equals B has unique solution x equals b times A inverse. And this is really proven kind of what we just did before. We're just going to take this, multiply both sides by A inverse, and pow, I get my answers. This is really, let's just look at it. AX equals B, which is, and B, of course, is equal to EB, but E is equal to A times A inverse times B, and then which is A times A inverse B. So we see that uh, that that X is equal. If you look at this guy here and that guy there, these two things are the same. That tells us, based on the previous theorem, that tells us that X is equal to, actually is equal to A inverse B, which is what we're trying to prove. And let's really, in a way, that's kind of what we do when we solve an algebra equation. We have 4x equals 9. We multiply both sides by 1/4, and we get x equals 9/4. So it's kind of like what this theoretical proof we just did is kind of similar to what we always did. Now, exponents, well, if you do repeated multiplication, now the star is not the multiplication that we know, but sometimes I just call it the multiplication, even though it's really not necessarily the multiplication that we know and love. But anyway, A star A is A squared, A star A star A is A cubed, and so on and so forth. A to negative 2 power is going to be A squared inverse. And all this stuff is very similar to the exponents as we know them. Now, if you have, if n is greater than or equal to 0, then A to the n is defined recursively. We say A to the 0 equals E, and A to the n equals A to the n minus 1 times A. And then from that, we generate all the different exponents. And some concrete examples, of course. Let's just look at this first one here. 5 to the third is equal to 5 squared times 5, which and 5 squared is 5 to the 1 times 5 times 5. So basically, which is 5 to the 0 times 5. So basically, 5 to the third winds up being 5 times 5 times 5, which, as we know, is 125. 5 to negative 3 is the inverse of 125, which is 1 over the multiplicative inverse, I should say, of 125, which is 1 over 125. And that's the story. Now, I want to point out over here that we use, in a sense, if we say A plus A plus A plus A 5 times is equal to 5A, that's kind of like the analogous to like A to the 5th power. Because if we're in a group and the operation of the group is multiplication, so A plus A plus A 5 times, which means we're operating A on itself 5 times. That's what we before we were calling that when the operation was just a random operation star, we were calling that A to the 5th power. So in a way, 5A is kind of the A to the 5th power. It's analogous. I don't know. It's different way of writing the same thing. Either way, it's a shorthand, right? And instead of writing A plus A plus A plus A, it's you write 5A. Instead of writing A times A times A times A, write A to the 5th. Anyways, here's a very important lemma. Lemma is a theorem, 11.3.13, which is that if G is a group and B is an element of G, n is greater than or equal to 0, then B to the n plus 1 is equal to B star B to the n. Hence, B star B to the n is equal to B to the n star B. We're going to prove this actually by induction. Remember our old friend induction. So B, the proof here of this lemma is I think it's pretty slick. So B to the first is equal to B to the 0 star B. Sometimes I say times, but I mean star. That's the definition of exponentiation. Now, B to the 0 is equal to E, so that's equal to EB, and EB is equal to BE because that's the way identities work. They're always commutative. And this E now gets replaced by B to the 0, so I see that B to the 0 times B is equal to B times B to the 0. That's my That's my first step of the induction proof. Now we want to assume the formula is true for some n greater than or equal to 0. So, and let's look at b to the n plus 1 plus n plus 1. That's going to equal b to the n plus 1 star times b, that's the definition of exponentiation. And b to the n plus 1 is b times b to the n times b, which is the induction hypothesis. And now we're going to switch to parentheses by associativity. Well, look what happened. I have b to the n star b, and by definition, that's b to the n plus 1. So I see that b to the n plus 1 times b is b times b to the n plus 1, which is exactly what we wanted to prove, and we did it. Yay! Let's see, we're almost done. Let's look at some basic properties here. A to negative n is equal to a inverse to the n. A to the n inverse is equal to a inverse to the n. A to the n plus m is equal to a to the n star a to the m. That's really interesting because we know that from real numbers. But now we're saying it's true in any group. And a to the n raised to the nth power is a to the. And these, by the way, these are properties of exponents that we know from. We know this from regular real numbers. We've done this a million times in high school or wherever. And now, whenever you first do exponents, and now we see it's true for a group in general. And this is a proof that these are all easy to prove. You can do them by induction, or if you have any other cool way. But let's get on to the biggie, which is the final theorem of this section, and that is this: if G is a finite group, if G is a finite group, and the order of G equals n, I mean the cardinality means there are n elements in this group G, and A is an element of G, then there exists a positive integer m such that a to the mth power equals e, and that is awesome. And m is less than or equal to n. That's awesome, meaning that if I keep on raising to a power, I'm eventually going to get to the identity element, which is a very, very awesome, powerful thing. So let's see if we can prove it. So let's just look at this list: a squared, a to the n plus 1. Now there's n plus 1 elements here of G that are on this list, but G only has n elements, so there's got to be some duplication here. There's got to be at least two of these that are equal to each other. So let's say a to the p equals a to the q, where p is less than q, and they're somewhere in this list. So we're gonna define m to equal q minus p. So a to the m equals a to the q minus p. But a to the q minus p, really by definition, is a to the q times a to the negative p. But a to the negative p is a to the p inverse. And a to the p inverse is equal to a to the q inverse. Why? Because we're saying, that's our assumption, is that we know that there has to be some duplication, and a to the p and a to the q are the guys that are equal. So that's how I got this step right here. But I have a to the q times a to the q inverse. Well, that's the identity element. So I see that the a to the m is equal to the identity element. So, and just to drive it home, since p is less than q and they're both less than n plus 1, q minus p has to be less than n. And that is fabulous. Fabulous. So we are cooking with two burners now. Bye, everybody. That's it for this video. It's been loads of fun. Here I am. I just want to show you, here I am in Hogwarts. And it's time for dinner soon. So that's it for this video, and we'll see you next time. Bye, everybody. Bye.